Where is everybody? All right. Good morning. Another day in isolation. Speaking of which, Will, remember isolation from from Halo 3? How'd you feel about that map? That was my first ever 30 kill game was on that map. I actually hate that map. Hey, how's it going? Morning, Nick. Surviving is good. All right, big day in the quotient topology. It's very exciting. That's fair. Yeah, it's pretty easy. All right, I think that is everyone then. Okay. Let's go ahead and get started. So I think we're actually going to cut a little early today, and then I'm just going to go live in Discord, maybe like the last 10 or so minutes to talk about project ideas. I think it'd be easier if we just talk in real time without the like 7-second lag to Discord. Um, so yeah, our goal is get through the stuff. I think we'll easily get through. Yeah, I think we'll get through everything. And then we can talk about those, and I'm also free until lunchtime, so we can talk for a while if you wish to. All right. Any questions on stuff before we get started with regards to quotient topology, or I guess topology in general? No? Okay. Sounds good. Let's get after it then. So our first thing we want to do, right? Okay, so first let's remind ourselves what is the quotient topology, right? So we have X with some topology, right? So this is our topological space. Doesn't really matter what the topology is. And then A is just a priori some set. Currently we have no topology on it. Then if we have some surjection onto A, then we can define U to be open in A, right? Clearly this is a subset of A, if and only if P inverse of U, the pre-image, is open in X, right? Which we can make sense of because X does have a topology, right? Nothing showing up on screen. That's weird because it's on correct. I don't know why there's a lag. That's weird. It shows up on my lonely screen. Okay. Let's see if that continues. I'll keep more of an eye on it. I'm not really sure what's going on, but I could like restart lonely screen or something here. Okay, so right, and then we call this the quotient topology. Yeah, that's not showing up. Okay, give me just a second. I'll just okay. This makes me sad. quotient topology induced by P. Okay. Now, is that working now? Seems like yes. Okay, cool. All right. So I think we'll talk more about kind of the issues with this and what I mean by like when is Q or P a quotient map, because sometimes, right, you do have a topology on A. You may not just be starting with some set you know nothing about, right? And so we'll talk about that here in a bit. But first, we want to show that this actually is a topology, right? And this is 169 for us. This is a topology on A. So how do we prove this? Maybe I'll say the first part. It's pretty easy, right? So we want A and the empty set to be open. I'll let you guys tell me about the open sets, or the union ones. So A and the empty set, well, the empty set is also the pre-image of the empty set, right? Because what maps to nothing? Nothing. And so this is open in X, right? Because the empty set is open in X. And then A, well, what is its pre-image? Well, these are just the things in X that map to A. Well, P is a function from X to A. God bless. Okay. So the question is why? So I'm not dropping frames. Is my audio fine? Like no lagging there? Okay. If it does it one more time, maybe I'll just restart. No, Mark, I changed my settings back, so I don't know why it's doing this because it hasn't done this for any of my like 20 classes before. Um, yeah, it's very strange. I mean, Zoom's gonna take longer because then I'd have to figure out how I'm gonna use this whiteboard in the same way. Okay, so P inverse of A is just X, which is open in X. So what about unions? Good. Right, exactly. So, start with some guy in A where the U alphas are all open in A. Then exactly what you said, right? So we have this theorem that tells us how pre-images work, and they distribute over unions, even arbitrary ones. And so this is the union of the pre-images. Well, each of these guys is open in X, and therefore X being a topological space, right? It's closed under arbitrary unions, and so I guess I don't need to say equals. So the union is open in X. And yeah, like you said, basically same for P inverse of the intersection, some finite intersection. Cool. Yeah, so basically we did the work way, way long ago when we first talked about images and pre-images in like our little opening chapter. Okay. Then let's actually get into some examples. So here we want this map onto a 2-point set from R. And yeah, by the way, if I say R without any indication of the topology, you can assume this is with the standard topology. Sometimes I'll say it, sometimes I won't. I will always say it if I mean like lower limit or countable complement, something like that. And so here we have the negative numbers go to A, and the non-negative numbers go to B. So then what is the quotient topology on this 2-point set induced by P? Say that again. So empty set, I heard. Yeah, I agree. So why is A in there but B is not? Yep. Whereas P inverse of A is open. Right. Yeah. And we should confirm here, right? So I mean, P inverse of the empty set is always going to be the empty set. And then, yeah, P inverse of our whole thing. We probably don't need to do this again after this problem, right? This is just kind of always going to be true. So, awesome. Okay. Um, Correct. Yeah. And it would be by that same argument as in the proof, right? So, yeah. And I agree. Once you know it's a topology, yeah, you know these things are in there. Sure. Good point. Okay. So, yeah, I mean, you guys already kind of told me what goes on here, but just for completionist's sake, because it's who I am as a person, um, we go to the 3-point set, and we send the negatives, the positives, and then just 0. And then remind me what was open? Yep, AC, and then of course, yes, empty set and the whole thing are open. Anything including B other than the whole thing is not, right? So yeah, I guess I don't need to write all the things that are not. These are all open, basically because you don't include the endpoint 0 on either of these. Good. That's fine. You get 0 points on the homework. Okay. I'm quitting. All right, so this was the interesting problem, I think. So this one, right, we kind of wanted to analyze it in 2 different ways. So we have one function, but in one case we are assuming a topology already on Z, and the other we are not. Okay, so this is the floor function. Yeah. What do you mean by that? When you say like it has a closed bound on both of them? No. So, right, like if I want to see what maps to x, it's going to be x, or we'll do integers, so we'll just say n to n plus 1, not including, right? So this is the greatest integer less than or equal to x. Right, and so once you hit the next integer, n plus 1, its floor would be n plus 1, so it's open on the right side. Yeah. And so, right, in our first little part here, the question is if I have the standard like subspace topology, which, what is that topology again? The subspace topology on Z induced by the standard on R? That's the definition, but we have a nice, yeah, discrete. Yeah, aka the discrete topology. So every subset of the integers is open here if is P a quotient map. And so this is where we're really working with the definition of quotient map, right? So I'm not inducing the quotient topology here. This is where I'm saying, right, P is quotient if and only if P is surjective, which it clearly is here, and P inverse of U is open if and only if U is open. Right, because I already have a topology on this set, and so basically I'm saying, like, does the quotient topology match the given topology, essentially? So what do we think here? I agree. Why? I already showed that openness doesn't hold. Ah, yes, I did. Why? I didn't really say anything about an inverse image, but I guess you're right. Right. So, I mean, right. Exactly. Yeah. So, I mean, you're right. I already did it. I just didn't put it in this notation. Yeah. And this guy is, as we have shown before, not open in the standard topology on R. Okay. So, yeah, this is not a quotient map. It does. Yeah, I agree. We'll get there in a second, but yes, 173 is now super easy. Pretty much. Sure. Yeah, absolutely. You can map the real numbers to dog, cats, and kittens and do a quotient topology on that. Yeah. The kittens get the negative numbers. They're open. Yeah, absolutely. All right. So then now, right, assume, well, you don't need to say assume necessarily, but let Z have the quotient topology induced by P. Right, and so here, once you induce the quotient topology by P, then that means that P is automatically a quotient map, right? Because you are defining the open sets exactly so that it is a quotient map. So in this case, what are my open sets? What do these look like? Are you sure? So I agree. So what Nick said, right, for those, right. So P of, say, ind n plus 1 open is, I think, what you're saying. This would still give me this. The problem here, right, is you're dealing with the image, not the pre-image, right? So it's still true that the pre-image of our singleton includes that endpoint. So this is still not open. Wait, why? Question. Yeah, go ahead. What do you mean by useful only for the standard? Whoops. Correct. Yeah. And so that's why Rippy said that 173 is really fast. So if I put the lower limit topology, then yes, I will get the discrete because all of these guys are open. So yeah, this is true because we're considering the standard here. Yeah. Right. Yep. Okay. So let me try to catch up with what you're saying. So you're saying if U is a subset of Z, then U is the union of singleton subsets, and so P inverse of U is the union of these guys here. And so we're saying, when is this open? Good. Okay. Yeah. So how about we write it like this, where n is some fixed integer, right? So basically, you're you're essentially thinking of it as like negative infinity to n intersect z, right? Is another way you could write this. All of the integers less than or equal to something. Oh, sorry, less than. Yeah. Right, but that is true by definition of this, right? Oh wait, no, I do want less than or equal to. Yeah. No, this is still 172, the second part. Okay. Yeah, so this is the only time, right? Because if you have some other union, if you don't go all the way back to negative infinity, you're going to include some endpoint, and so it's not going to be open. So basically, you have to go all the way to the left, and then, yeah, you get exactly what you want, right? Because the union over m less than n less than or equal to n of, say this guy, right? This is the pre-image, is going to be equal to negative infinity to n plus 1. And this is obviously open in R. But this is the only way you will get things that are open in R. So if you remember from your exam, your take-home exam here, this is basically like the left ray topology intersected with Z, or the subspace topology on Z induced by the left ray topology. So that's kind of cool, and a little weird. I expected that to be somewhat challenging. Yeah, so if it's not infinity, then that means there was some smallest thing that you included, and you're going to have a closed endpoint, and so that's not going to be an open set in R. Yeah, because that guy won't be in the interior. Okay, so you guys have already told me that 173 is super easy, except to write. So again, same map, the floor function, x goes to the floor of x, but R with the lower limit. And as you said, this is discrete, right? So I think it's easiest to use this, right? Because like you want to do just the singleton sets, and then yes, these are the basic opens. And then we know that all the singletons being open is enough to show it's discrete, right? We don't want to do like a general open set. Or maybe that's not what you meant, but that's what it sounded like to me. Cool. Okay, so quick poll. How many people actually had time to think about 174? Nice. Okay, so we have some thoughts. 174 is an interesting one. That means a lot to me, Devin. It means an awful. Or was that Riley? I didn't even see. Sorry. What, Rippy? I have not looked at your homeworks yet. I was pretty busy last night. Uh, yeah. Wait, no, it's still a function. What do you mean by that? Both of these things? Right, because this guy is specifically for non-integers. It maps to like the next odd integer kind of thing, and then any integer maps to an even. Jack, can you use headphones, man? Shoot. Mm-hmm. Yes. Yeah, intersection of opens will still be open. I am confused. I don't think so. You shouldn't be looking back in R. You should be looking at the integers and then mapping back with the pre-image. So like the fact that you look at these guys or something, this you don't start here. You start with like p inverse of 1 and then you get the interval from 1 to 2. Right? Like I mean this is a proof in and of itself. Because I mean it is a topology. It's the quotient topology. We know it's a topology, so it's got to be closed under finite intersections and arbitrary unions. And it's also because if you do intersections or unions of things like these, you will get still open sets in the lower limit topology. Does that make sense? Okay, cool. Yeah, so for this one, right, like we're mapping whatever integer to double it goes to an even integer. Okay. Yeah, I think you can draw cool pictures with this for sure. Yeah. Yeah, it is cool if you draw it. Yeah, you have these strips, as you said, of width 1 that map to like an odd, and then this even or integer just goes to an even, then you have another strip. And yeah, it is pretty interesting. Well, let's just kind of get into this. So the first question, right, was along the lines of 172, like is P a quotient map if we consider Z with the discrete topology, the subspace topology. Indeed, one word answer, no. Uh, what is not open? Right, so the evens all have pre-image of a singleton set. It's the odds that can have nicer things. Yeah. Yeah, so this works. any even works here as a counterexample. Okay, so it's not a quotient map, but of course, that's just if you have the discrete topology. So then the question is like, okay, if I want this to induce my quotient topology, what do I get, right? So what is cool? Yeah, it is the digital line topology. Fancy. How did you show it, Nick? All right. Fair enough. Okay. Okay. Hit me with it. Ah. Okay. Yeah, here. Okay, so let's okay, so like our general odds, so you're saying, I don't know, do you mind if I write like k plus 1, how do I want to write this? The union of these such that 2k plus 1 is in AO. How about that? Okay. I don't know a more concise way to write it. Oh, okay. Gotcha, gotcha, gotcha. Okay. Um, I don't think it matters either way, right? Okay. And so here I will say the k such that 2k is AE to be consistent. What? You can. I can write in pink. Colors. All right. Oh, yeah, no. Okay. So, how can we manipulate this into something more useful? So, or like, what is the use of this? Mm-hmm. Yeah, so maybe I'll make a note here, right? P inverse of 2k plus 1. Again, this is always abusive notation, right? I mean, this is technically the set. I've been doing this earlier. Is k to k plus 1. So any odd in Z is open? Yes. Yep. Yeah. And so this is open too. So this right here, right, this tells us immediately that every basic set, every basic open in the digital line is open in the quotient topology here. So basically that tells us that the quotient topology is finer. Yeah, that would be. Well, not necessarily 92. This is, you'd have to go a little bit. It's more just by the definition because I don't have a basis for the discrete, or sorry, for the quotient topology, and so it's not exactly an application of comparing bases, but rather any open set in the digital line is the union of basic opens. All of those lie in the quotient, and so any union of those would lie in the quotient. And so the quotient is finer. But again, not strictly finer here. But we have to show that. Correct. But I think like this can kind of help up here a little bit for the other. Right, so we would want to show digital line is finer than the quotient topology. And so here, I think it's easier, right? So let me name these. Let's just say like ZD is the digital and ZP is the quotient induced by P. Then I want that the digital line is finer, right? So I want this. And it's a little bit harder to just think of, say that again, Rippy? Correct. Yeah. And so our goal here is to have that not be true. We don't want it to be strictly finer. Yeah. So I think kind of what Devin was saying is how you can figure it out. So basically, the way I think of this is to use the contrapositive. Although you don't have to, I don't think. But that seems easier for me. So like suppose CD, oops. Uh, so suppose we have something, or I guess, yeah, I will show if something is not open in ZD, then it's also not open in ZP. Some U not open ZD, we show U is not open in ZP. For me, this is easier to think about. You know, your mileage may vary on that. So the way I think of this here, if you know something is not open in the digital line, what does that mean? So we know all of the odds are open in the digital line. So like the odds aren't the problem, right? And you have some union, right? U is again some union like Devin had, right? So it's like some, well, I guess maybe I'll use his, he said A. So UO for U odd plus UE. So this is fine, right? This is open because all of my odds are open. So like this is where the problem lies. So what do you know about U, or specifically the evens in U, if U is not open? Yes, so if U is not open, some 2k in U such that, we'll say without loss of generality, 2k plus 1 is not in U. There's some odd that's not in there. Okay. Why is this good? Well, that's true, but okay, so that's why it's not open in the digital line. Why must this not be open in our quotient topology? Pretty much, yeah. So for me, I guess the real issue, yeah, no, this is fine, right? So P inverse of 2k, right, would be whoops. Kind of, yeah. So we know this is true, and basically since 2k plus 1 is not in U, we're going to get, we don't have k to k plus 1 in P inverse of U. And so basically, it depends on whether or not you have 2k minus 1. Yeah, so basically our case is, and it doesn't really matter, right? So basically we have, you know, either just k or k minus 1 to k, but including k inside U, but that's not open in R. Yeah, so that's the idea. Basically, you have some endpoint that must be included, and that's a problem. Cool. I think that's a really cool problem. 175 is somewhat similar in terms of like how you would approach that, and I'll leave that to like a problem set problem. But yeah, I think that's kind of neat how you get the digital line topology there. I'm sorry, Rippy. We will still have problem sets. It's not a bad problem. They're going to be more chill because we're doing things online. Like, trust me. But not easy. Good. The trust makes me drunk with power. All right. So I'm just kidding. All right, there are a lot of horrible, horrible jokes I can make that would get me banned on Twitch here, so I'm gonna not make any of them. Okay, so for what? I've said nothing. Okay, so the next thing that we're going to talk about is kind of, remember we started the quotient topology section with talking about things like this, and you're just like, ah, cool, if I glue this, I get a circle. And this seemed to have nothing to do with what we've been doing, right? We have just like pre-images, we make quotient topology, I see no gluing, what's happening? So we want to talk about like how does this gluing actually come up? So where does gluing come into quotients? I don't know if my old office mate Mark is still watching, but this is a great time to quote our advisor, who I hate horribly, but he did have a good line. He was a very German man. Instead of saying come into play, he would say come into the play. And I was just like, I don't think anyone's acting, but all right. That's my whole story. Right. So basically the idea here is equivalence classes. Okay, so here we would say that like this guy is going to be the set of equivalence classes given this equivalence relation given by this gluing, right? You glue equivalent points, so we would say like A, it's equivalence, so it's reflexive. A is going to be equivalent to A there. We glue it, and then all of the other points are not equivalent to A. Nice. Come into the play, man. We always love it. Specific ethnicity. Jeez. It's a tough crowd. I had to quit Twitch. All right. So I'm just going to follow the notation that we're going to use here. So this is going to be our quotient space. So this is really kind of another way, but we'll see that these are equivalent really. So your quotient space, yep. All right, there we go. X mod tilde, and this should not be surprising notation, right? This is exactly like you had with groups, with quotient groups, right? We'll use X mod whatever. And so where this is an equivalence relation. Right, and so really what we're saying is X star is the set of all equivalence classes in X. Right, so basically you glue together equivalent things, and that's what you end up with. So, how is this similar? Right, how do we see this as like a quotient map? Well, we have a natural quotient map here. So we have a natural, or I guess a natural surjection, and then you can of course define the quotient topology. There is indeed a universal property. We have a natural surjection P from X to X star. What do you send X to? Exactly what you think you send X to. The equivalence class corresponding to X. It's really knowledge of the past, Rippy. Universal properties have been studied for a long time. Okay, so let's just see an example here and just kind of get after it. Okay, so here we'll have X be the first 5 numbers, depending on whether you think 0 is a natural number or not, which even I honestly waffle on, depending on the situation. For cardinality's sake, I like counting with the positive integer, so that's why I chose not to include 0 for this class, but in general, I think I do include 0. And then we have some topology given by this, basically just unioning up things containing 1. This is exactly the particular point topology with respect to 1, right? Then Yeah, I agree. It is a way to count things. It just helps with the bijection when you're like doing things from the natural numbers. You usually index starting at 1. It's like the more natural thing. So yeah, it was definitely just a choice, and it is something that people differ on quite a bit. So it's a reasonable choice. Okay, and then define this via the classes 1 is equivalent to 1 and 2, and 3 is equivalent to 3, 4, and 5. And if you are dismayed at the fact that I have not given you a specific relation, or seem like this may not be an equivalence relation, or that I should justify this, you should remember that a partition of your set into equivalence classes like exactly is equivalent to having an equivalence relation. So the fact that I have a partition here tells me that this will definitely be an equivalence relation. So what is my topology on X star? And right, X star only has the elements 0, 0, 1, and 3, these equivalence classes. Oh yeah, it's not the particular point topology. I'm a big dumb. Yeah, thank you, Mark. Good point. Sorry, say that again, Rippy. No, the map would still be, right, I mean, P is still defined as X to X star, where X goes to X. So, I mean, you still define it on points, not, this is a set, a function from X, not from the power set of X. Yeah. No, 2, 3 doesn't map to anything. 2, 3 is not an element of X. Or I guess, like, yeah. Correct. Yeah, 3, 4, and 5 all go to the equivalence class 3. Okay, yeah, so you're just saying, like, sure. So you're saying P of 2, 3, which is, yeah, the union of those two. Yes, okay, yes, I agree. So this would be X star, sure. Right. Right, but I mean, you shouldn't be looking at like forward images, right? I mean, yes, but again, we shouldn't be thinking about forward images. I don't think that's true. Sounds like a great pearl of wisdom, but here I would much rather you just think backwards, because how do we define our quotient topology? Yeah, in terms of pre-images, right? So like if I want to know what my topology is on X star, right? I mean, you only have so many sets, right? There's only empty set, there's a singleton set of this equivalence class, the singleton set of this equivalence class, and then the whole thing, X star. So like what of these are open? Why? Okay, why? Okay, so I guess since I'm not hearing it, so I mean this is 1, 2, 3, which is in T, right? So this is open, right? So 1 is open. 1, 2, sorry. Yeah, sorry. Okay. And then P inverse of 3 is 3, 4, 5, which is not in T. So 3 is not open. Well, it exists, it's just not in T. And then we already know these guys are going to be open. The two equivalence classes. X star is these two equivalence classes. Yeah, X is the big space, you mod out by your equivalence relation, you're left with the equivalence classes. That's your X star. Five. I mean, the preimage of X star is always going to be all of X. 5 maps to the equivalence class 3 as well. Right, my equivalence class 3 is all the remaining things. Oh, yeah, no, 5 is definitely there. Okay, so I want to talk about one last one. I want to get started on it. I'll let you think about the rest of it. I want to talk about 1 and 3, but not necessarily 2 yet. So this is on 177, mostly because we've really already seen this. So if I say 0 is equivalent to 1, and then x is equivalent to x for all things in between, then first, what are my equivalence classes? And what does x star actually look like? Thoughts? Okay, so it sounds like you're saying that these are equivalence classes, right? So those guys get glued. And then this says that all of the other things just glue to themselves and nothing else, right? So then your other equivalence classes are just X, singleton equivalence classes for all X in 0, 1. And so, yeah, exactly. What you get is the loop, where this is the equivalence class of 0, and then the rest of the points are all still there. We just kind of taken our endpoints and glued them and done nothing else. Yeah. No, that's a good point. So I mean, that's something very, very special about quotient groups, right? And yeah, cosets all having the same cardinality is like a very special property, and we've really only seen these in group theory, right? So quotients in general, like modding out by an equivalence relation is something very, very common. And in general, equivalence classes definitely need not have the same cardinality. The quotient groups are actually a much more special thing going on. This is the much more uh, on average thing that you will see. But that's a good point. Yeah, it's very, very different from what we saw there. Yeah, I think so. I would say that, yeah, I think that the quotient being thought of as gluing really in any case is pretty much true. Again, some are more difficult to visualize. I mean, gluing together your cosets, all the like group elements in a single coset is, I think, harder to visualize than gluing together two endpoints of an interval to make a loop. But yeah, gluing in general, I think, is the intuitive idea, and equivalence classes are exactly the way that you would formalize that notion. Yeah. What if you take the quotient of a topological group? You know, topological groups are actually one of the project ideas, Mark. And, you know, being the group object in the category of topological spaces is kind of cool. It is more than that, and we can talk about that right after we end stream here, because that is indeed one of the ideas. But yeah, topological groups, it's more than just a group with a topology, because for instance, you could always put the discrete topology on any group. It's a topology on which your binary operation and the inversion maps are continuous maps. So it has a little more structure than just any topology. It is a topology where the main things you would do inside a group behave nicely. All right. Yeah. Hmm. Right. So that, right, you would just define your equivalence in a different way, right? So I mean, I don't really specify a direction at all. I'm specifying what the points are. So I mean, this is getting a little ahead of ourselves, I guess. But um, if you see this, then that means when I define my equivalence relation, right, and I take a point here, instead of like on the cylinder or the torus where I would glue to this guy over here, I don't do that. Gosh dang it, why did it take away the whole line? I'm going to glue to the guy down here. And, you know, if I have a guy over here, I will glue to this guy. You have the freedom to define your gluing. So, like, you don't specify, like, an orientation, but yeah, you would just do it like that. So, like, something like X is equivalent to, what? Oh, something like X is glued to 1 minus X for all X. Like, these are the guys over here. Yeah, yeah. It's not formal. You'd really want to do ordered pairs, but yeah. All right. So let's go ahead and in stream, and then we still have class, but I just want to be able to go live and talk to you in real time about projects. So if you want to bring up that list on Canvas or whatever, we can talk about whatever you want to talk about, and it'll be fun. All right.